Hello friends, this video is brought to you by www.moeteaching.com.
Let us read the question. Show that 3 root 2 is irrational. Note that we mentioned in class 9th that product and quotient of non-zero rational and an irrational number is irrational. Here we shall prove it. Let us assume to the contrary that 3 root 2 is a rational number. If it is rational number, then there exist co-prime integers a and b where b is not equal to 0 such that 3 root 2
Hello
should
friends,
be equal to
this
common factor of if we multiply into 3. Let us solve this further. We can get root 2 equal to a by 3b. Now look at the right hand side of this equation. Since a and b are integers, a by 3b will be a rational number, and we are saying that root 2 is equal to a rational number. We write that this would imply root 2 is equal to a rational number, but this contradicts the fact that root 2 is irrational. This contradiction has arisen because our assumption was incorrect that 3 root 2 is a rational number. So we conclude that 3 root 2 is irrational. Here we have a theorem which says that if x is a rational number whose decimal expansion terminates, then x can be written in the form p by q, where p and q are co-primes. That is, they don't have any other factor other than 1 common between them. And the prime factorization of q is of the form 2 power n, 5 power m, where n and m are non-negative integers. Don't worry, we will explain this theorem through examples. So let us proceed. We have studied in our class 9th that when we convert a rational number into decimal, it can either be a terminating decimal or it can be a non-terminating repeating decimal number. Let us consider some terminating decimal numbers. Say we have 0.375. This can be written as 375 by 1000, which is equal to 375 by 10 cube. Let us now try and cancel the common factors between the numerator and denominator. We can expand 375 as 3 into 5 cube, and 10 cube can be written as 2 cube into 5 cube. So 5 cube gets cancelled and we are left with 3 by 2 cube. Let us take another terminating decimal. Say we take 0.0875. Let us convert it into rational. Factorize this further. We get 5 cube into 7 whole by 2 power 4 into 5 power 4. Now let us cancel. 5 cube gets cancelled and 1 5 is left in the denominator, which is equal to 7 by 2 power 4 into 5. In both these numbers, it appears that we have converted a real number whose decimal expansion terminated into rational numbers of the form p by q, where p and q are co-primes, that is, they do not have any other common factor other than 1, and the prime factorization of the denominator has only power of 2 or power of 5 or both. We should expect the denominator to look like this, since power of 10 can only have powers of 2 and 5 as factors. Let us take another example. Say we take 0.104. This can be written as 104 by 10 cube, which can be written as 13 into 2 cube by 2 cube into 5 cube. Now 2 cube gets cancelled and we get 13 by 5 cube. So here the denominator is only power of 5. Likewise, you can take up more examples and see that any real number which has a decimal expansion that terminates can be expressed as a rational number whose denominator is a power of 10. Also, the only prime factors of 10 are 2 and 5. So, cancelling out the common factors between the numerator and the denominator, we find that this real number is a rational number of the form p by q, where the prime factorization of q is of the form 2 power n 5 power m, where n and m are positive integers. So now if you read the theorem, you will understand it more better. It says that let x be a rational number whose decimal expansion terminates. That means it is one of the terminating decimals. Then x can be expressed in the form p by q, where p and q are co-primes. We have done in each of these cases. And the prime factorization of q is of the form 2 power n 5 power m, where n and m are non-negative integers. Now the obvious question arises that if we have a rational number of the form p by q, where q is of the form 2 power n 5 power m, then can we say that p by q will have terminating decimal expansion? So let us try and reach a conclusion. Say we have any rational number 3 by 10. Then since b or the denominator is a power of 10, we know that it is going to be a terminating decimal. You can take any other number. Say we take 375 by 10 cube. This will be 0.375. That is again a terminating decimal. And similarly we can take 7 by 10 square. This is equal to 0.07, which is again a terminating decimal. From here we conclude that any rational number a by b where b is a power of 10, that is denominator is a power of 10, will have a terminating decimal expansion. So now it seems to make sense to convert the rational number p by q, where p and q are co-primes and q is of the form 2 power n 5 power m, to an equivalent rational number of the form a by b, where b is a power of 10. Let us see how we can do it. Say we have a rational number 3 by 8. Now here 3 and 8 are co-primes. We can write it as 3 into 2 cube. We can multiply and divide by 5 cube and get 3 into 5 cube whole by 10 cube. So we have converted 3 by 8 in the form a by b, where b is a power of 10. Let us solve this further. We have 375 by 10 cube. This gives us 0.375, which is a terminating decimal. Let us take another example. Say we take 7 by 80. This is 7 by 2 power 4 into 5. Our p by q is 7 by 80. We are trying to convert it into a by b, where b is power of 10. What we can do is multiply by 5 cube the numerator and denominator to get an equivalent fraction. This gives us 7 into 5 cube whole by 2 power 4 into 5 power 4, which is equal to 875 by 10 power 4, and we get a terminating decimal 0.0875. These examples show us that we can convert p by q, where q is of the form 2 power n 5 power m, to an equivalent rational number of the form a by b, where b is a power of 10. Therefore, the decimal expansion of such a rational number will terminate. So we come to the conclusion that if we have a rational number x of the form p by q, where q can be written in the form 2 power n 5 power m, where n and m are non-negative integers, then x has terminating decimal expansion. Now let us look at non-terminating repeating rational numbers, or in short called recurring rationals. One such number can be 5 by 3. If you divide it, you will find that its decimal expansion is 1.666 and so on. So that is non-terminating repeating rational number. This is also written as 1.6 bar, showing that 6 is repeating. Another example is 17 by 6. This is 2.8333 and so on, which is equal to 2.83 bar. Clearly here we can see that the denominator 3 is not of the form 2 power n 5 power m. Similarly, 6 is also not of the form 2 power n 5 power m. Let us see another example. Say we take 1 by 7. Its decimal expansion is 0.142857 and so on. Here also the denominator, that is 7, is not of the form 2 power n 5 power m. Therefore, by the previous two theorems, that is theorem number 5 and theorem number 6, 1 by 7 is not going to have a terminating decimal expansion. This brings us to theorem 7, which says that let x equal to p by q be a rational number such that the prime factorization of q is not of the form 2 power n 5 power m, where n and m are non-negative integers, then x has non-terminating repeating decimal expansion. That is, then x is supposed to be a recurring rational number. And we can conclude that the decimal expansion of every rational number is either terminating or non-terminating repeating. We will see how theorem 5, 6 and 7 will help us find out if the rational number is terminating decimal expansion or has a non-terminating repeating decimal without actually long division of numerator by denominator. Now suppose the question is, without long division find out whether the rational number is terminating or recurring. Our first step would be to prime factorize the denominator. We get 17 by 2 cube. We can write it as 2 cube into 5 power 0, as anything to the power of 0 is 1. So now we have a denominator of the form 2 power n into 5 power m, where n is equal to 3 and m equal to 0, that is non-negative integers. So by theorem 6, 17 by 8 has a terminating decimal expansion. Here we can also find the number of places of decimals after which the decimal expansion terminates. For example, we can write equivalent rational number of 17 by 2 cube as multiply and divide by 5 cube, which will give us 17 into 5 cube whole by 10 whole cube, and this would mean that the decimal will terminate after 3 places. We write that the decimal expansion of 17 by 8 terminates after 3 places of decimal. Let us take up another example. Say we take a rational number 29 by 343. Let us prime factorize the denominator. It comes out to be 29 by 3 power 5. Clearly, the denominator is not of the form 2 power n 5 power m. So we conclude that the decimal expansion of 29 by 343 is non-terminating repeating.